So far, when talking about colligative properties, we're focused on solutions where the solutes are non-volatile. Okay, so what we're going to do now is we're going to look at solutions where the solutes are volatile. And again, what did we say a volatile solute is? Something that's volatile is something that ordinarily exists as liquids or gases in pure form. Okay, the non-volatile solids would ordinarily be solids under ordinary conditions. Now, for example, let's take a look at a mixture of two liquids. We can define what's called an ideal liquid mixture as one where both components of your mixture obey Raoult's law. If you remember what was Raoult's law, if A is a component of my mixture, like my solvent, okay, the partial pressure or the vapor pressure of A, that would be in equilibrium with my mixture. So if I have liquid right here, a mixture of A and B, okay, in the gas, I also have A and B since A and B are both volatile, right? So the partial pressure of A in the gas would be equal to its partial pressure if it were pure multiplied by its mole fraction in the liquid phase. So this is Raoult's law, remember? So Dalton's law of partial pressure says that the total pressure of your gas mixture is just the sum of the partial pressures of the components. So the total pressure above your liquid that will be in equilibrium with your liquid is just the sum of the partial pressure of A plus the partial pressure of B. So you can see P star B times X of B, that's the partial pressure of B, and P star A times mole fraction of A is the partial pressure of A. Okay, so that's what we would expect if we have what's called an ideal solution, where ideal mixture of two liquids where both components of your mixture obey the Raoult's law. Okay, so most components in fact do deviate from Raoult's law when their mole fraction is significantly less than 1. In those cases, we say they typically obey what's called Henry's law. But let's look at Raoult's law first. Let's look at the consequences of Raoult's law if both components of your mixture obey Raoult's law. Okay? So let's look at this question right here. At a given temperature, pure liquid A has a vapor pressure of 80 torr. What does that mean? That means P star A is equal to 80 torr. Okay. And pure liquid B has a vapor pressure of 100 torr. So that means P star B, the vapor pressure of pure B, would be 100 torr. Now, let's say you were to mix 0.2 moles of liquid B with 0.8 moles of liquid A. Okay? So you have a liquid that has 0.2 moles of liquid B and 0.8 moles of liquid A. What would be the vapor pressure of the resulting solution? Let's see. The vapor pressure would just be equal to PA plus PB, right? Partial pressure of A plus partial pressure of B. So it's going to be P star A times mole fraction of A plus P star B times mole fraction of B. Okay, what's the mole fraction of A and B in this case? So this is going to be P star A is what? 80 torr times mole fraction of A plus P star B, which is 100 torr times mole fraction of B. How do we solve for the mole fractions? Formula for mole fraction? Mole fraction of A is moles of A over total moles. How many moles of A do we have? 0.2. And our total would be, oops, nice. Moles of A is 0.8, sorry. And what's our total moles? What's 0.8 plus 0.2? 1. So mole fraction of A is just 0.80. What would be the mole fraction of B? 1 minus 0.8, or you can say moles of B over total moles, which is 1.00, is going to be 0.20. So let's plug those numbers in. Mole fraction of A is 0.8. And mole fraction of B is 0.20. Okay. So you can see that the vapor pressure of A is lowered, right, to 80% of what it was. The vapor pressure of B is also lowered to only 20% of what it would be if it was pure. And so what's the total pressure here? Go ahead and calculate that, and collect the answers A, B, and C. Is it between 80 and 100 torr, greater than 100, or is it less than 80? Ready? Or do you need time? No? Need one more clicker. Okay. Answer is between 80 and 100. Okay? In fact, if you were to make a plot of this, it's a way to visualize this. If you were to plot, okay, versus mole fraction, okay, mole fraction of A from 0 to 1, okay, what would be the vapor pressure of A? And let me put that in red. Versus mole fraction of A. P sub A is equal to P sub A star times XA, right? So when mole fraction of A is 0, what's the partial pressure of A? It's going to be 0, right? If XA is 1, what would be the partial pressure of A? It's PA star, right? And what is PA star? That was 80 torr, right? This is PA star, which is 80 torr. And so if you were to plot that, this is what you get. You just get a straight line, okay, for that. What would happen if we were to plot partial pressure of B versus mole fraction of A? What did we say partial pressure of B was? P star B times XB, right? Which is P star B times 1 minus XA. Remember, XB is 1 minus XA. Mole fractions add up to 1. So that's equal to P star B minus P star B XA. Okay, so when XA is 1, when XA is 0, if this is 0, what is my partial pressure of B? It's just P star B, right? And what is P star B? It's 100. So when XA is 0, it's going to be 100. That's P star, that's PB. And when it's pure A, when XA is 1, what is P star B minus P star B? It's going to be 0, right? So if you were to plot the partial pressure of B versus mole fraction of A, it's going to look like this. It's going to be a straight line. So if you add these two up, okay, what you'll get, so if you add the black and the red, what you'll find is you just get this straight line right here. So a mixture of the two will have a vapor pressure that's in between. Okay, so that would be the consequence of both liquids following Raoult's law. Now, they're not necessarily going to follow Raoult's law. Like I said, there tends to be deviations from Raoult's law. We're not going to get into that. This would be the ideal case. All right. How about this one? At a given temperature, pure liquid A has a vapor pressure of 80 torr, while pure liquid B has a vapor pressure of 100 torr. Same example as before. In a liquid of mixture of A and B, the mole fraction of B is zero point 0.2. What would be the mole fraction of B in the vapor? In the liquid, it's 20% B. In the vapor, is it still going to be 20% B, less than 20% B, or is it going to be larger than 20% B? Let's try to use some common sense here. Which one's more volatile, A or B? Vapor pressure of A is 80 torr. Vapor pressure of B is 100 torr. Which one is more volatile? More volatile has a greater tendency to be in the gas. So, vapor pressure gives you an indication of volatility, right? The higher the vapor pressure, the more volatile. So we say B is more volatile, right? So if it's only 20% B in the liquid, in the gas, you would expect more than 20% B. Okay? So it's going to be larger than 0.2. Let's actually calculate that. Okay? P sub A is how much? Is P star A times mole fraction of A. And what's P star A? 80. What's the mole fraction of A? It's 0.2, right? No, that's B, so that's 0.8. What is 80 times 0.8? 8 times 8 is 64, so 64.0 torr. What is the partial pressure of B in the vapor? P star B times mole fraction of B. What's P star B? 100 torr. What's the mole fraction of B? 0.2. What's 100 times 0.2? 20 torr. Okay. How do we get the mole fraction of B in the vapor? Mole fraction of, so we don't confuse it with the mole fractions in the liquid. We're going to use a different letter. Okay, we're going to use Y for mole fraction of B in the vapor. So Y sub B is mole fraction of B in the vapor. Okay. And if you remember your earlier class, Chem 105, what would this be? This is just going to be partial pressure of B over the total pressure, right? So that's going to be equal to 64.0 over 64.0 plus 20.0. P total is just PA plus PB. Okay. So this will be 64.0 over 94.0. What's 64 over 94? Not 94, 84. 64 divided by 84, it's 0.76. Oh, I'm sorry, it's not 64. Partial pressure of B is 20. Okay, sorry about that. This is 20.0. Okay, so this is 20.0 over 84.0. You can see that is, oops, 20 divided by 84, small fraction is 0.238. Okay? That's as expected. We expect our vapor to be richer in the more volatile component compared to the liquid.